and looked at all the talk abstracts and organized them ahead of time. So let's see if we can put all our talks into categories. And there's different ways we can put, especially the experimental talks today, into categories. And one way we could arrange them by saying, well, you know, we're in the business of looking for physics beyond the standard model, mostly using very precision measurements. It's all very well that we can make a measurement of 15 digits, but we have to compare it to something. So how do we do this comparison? How do we compare our precision measurement results to the standard model value? And there's different ways of doing it. And that's one way we can sort of divide things up. So one thing is differential measurements. Think of the king plots we've already heard from. If you do a differential measurement, maybe most of the standard model contribution will subtract out. Time varying measurements are actually a sort of differential measurement. Let's measure something today and compare it with what we measured yesterday. The difference is also a differential measurement, isn't it? And hopefully in the standard model, these things don't change. And so there's a way of getting at it. There are experiments, I don't think we'll be hearing about it today, where one of sort of natural Coulombic, one over R squared type forces naturally cancel out. You can design, if you design things cleverly, and that's a way of suppressing the standard model contribution. I'm putting this in quotes, easy to calculate standard model values. Basically, if you have only leptons and photons, or mostly just leptons and photons, and I'm really just, in this particular case, I'm only really thinking about G-2, you can, not fully easily, but with a great deal of effort, calculate things in the standard model to 12 some digits, something like that, and subtract it that way. And that's, so we just heard about that, and we'll hear more later in this session. And then there are looking for forbidden effects which are either zero or near zero in the standard model. The standard model makes no allowance for fractional charge, no allowance for spin statistics violation. The standard model, there are no poltergeists. What do I mean by poltergeist? A poltergeist is a ghost, and it's a ghost which is so thin and tenuous it could pass right through the walls of your house into your house. Now, an ordinary ghost, after it's passed through the walls of your house, is so ethereal, so tenuous, it cannot pick up a pan. Its hand would pass right through your pan. But a poltergeist is a particular kind of ghost who can first pass through the walls of your house and then pick up a pan and bang it in your kitchen and wake you up at night. Now, in German, this is called a poltergeist. In every other language, it's called a wimp. Okay, so this is all right. Then there are violations of PT and so on, and that's particularly what I'm going to be talking about today. Is experiments which violate CP symmetry, which is a pretty strong symmetry in standard model physics. So the effects we'd be comparing with are very small. Another way of sorting out of like separating all the talks we heard today is by seeing how they fit in relative to how the hypothetical new physics we're looking for might fit in relative to the standard model of physics. Everybody has a favorite graphical, visual representation of the standard model of physics. I made my own for the purpose of this talk. Here's the standard model. On one axis, we have strengths of interactions with the other standard model physics. This is not all the particles, but it's many of them. On the other axis, we have mass. So we have top quarks, which are strongly interacting because they're QCD particles, but that's a very heavy one. A neutrino is very weakly interacting and very light. A graviton is still lighter and still more weakly interacting. So we can scramble we can arrange all the particles there, and I can ask, well, where are the other particles? If there are new particles which aren't part of the standard model, where might they be? And we can put them into general categories. Again, we're sort of in the mode of categorizing things. There are particles which are too sneaky for us to see because they're not particularly massive necessarily, but they're very weakly interacting. They're the sly particles. Then there's the fat particles, spelled with a PH, meaning that not only are they very massive, but they're also awesome, right? And then there's particles which are both, and those are the WIMPs, basically. Actually, think WIMPs actually mean weakly interacting massive, so it basically, by its very name, we know where we put it on this plot. Okay, how would we find these particles? Most of the talks that were experimental talks that we'll hear today are in this category. There are many, many different sort of efforts to see weakly interacting exotic particles. Fifth force, time varying constants. Generically, dark matter searches tend to fall into this category. There are the famous WIMP sort of poltergeist type searches going on like that. The standard way for many years of looking for the very massive particles with colliders. As we make more and more massive colliders, they have to be both more energetic colliders, but also The colliders themselves don't actually have to be more massive. The particles, I mean, they have to be more energy in the colliders, although they tend to go together. LHC is a very massive experiment. But we should note that it has to not only be more energetic, but also brighter because cross sections go down. Anyway, they're building in bigger and bigger ones, but the cycle time now is heading toward the vicinity of 30 or 40 years. So the next one here won't be along for a while. There is some sort of exclusion from the LHC. It's on the order of 2 TeV. It's model dependent. It's basically everything is model dependent, and this exclusion that, but it's got a slope to it. If the particles are more strongly interacting, probably we're more likely to see them in the Large Hadron Collider. Weakly interacting, we can only see we can't see as massive particles. Okay. And to this world comes the dipole moment searches. And so really the dipole moments experiments and in the world of precision, they are the experiments which most directly go head to head with the colliders in the sense that they're looking for the zone up here. Kind of to summarize here, there's I got the red zone here and the green zone where we're looking for new physics. The strongest motivation for looking over here is the observational fact that dark matter exists. The actual way you see it, as we will hear in this workshop and elsewhere, there are many different ways of getting at this. The strongest motivation for looking over in the fat region, well, there are traditional high energy physics arguments having to do with extending up to unification of forces, various naturalness arguments. The antimatter asymmetry, another observational fact where all full of protons and all full of antiprotons, tells us there has to be more CP violation, and this seems to be like a good place where it might be. So there's various motivations to look up here. The experiments, future accelerators, they're quite a bit far off, and right now we have the dipole moment. Anyway, putting things in context. It's sometimes I hear a lot of talks and I try to think like, what do these talks all have to do with each other? Try to put them all together into one collective picture. I'm here today to talk about precision measurements of lepton moments, both G-2, by which I mean magnetic dipole moments, and electric dipole moments. Experiments I've been doing now for many years, always jointly with Jun Yi, my dear colleague from JILA, and we've been working on this project together for 15 years more, basically. So we've been doing this for years and years. I am a relative newcomer to particle physics. I will today make assertions about particle physics. You should not take them too seriously because I'm kind of like an AI thing. Like I listen to words that are strung together and I restring them together. And so this is sort of the AI version of particle physics. And there may be corresponding ludicrous things that come out of this. But I'm basically saying, John Doyle taught me a lot of things. Matt Reese here at Harvard read papers from Rancy Bulsoff. And if I get it right, it's because of them. And if I get it wrong, it's because of my own inadequacies. But let me know if I do get it wrong. This is the group as it's currently configured. June and I, and these are the grad students currently working on the group. And I see there's someone missing there. Who is missing from the picture? Oh, yeah, it's you out there. We are looking for a postdoc. Let me or June know. But you can see, I don't know if this is what you look like, but you know, I'll fix the picture. We had to Photoshop June in because he wasn't there on that day. Well, we can put you in there too. Well, actually, so why am I talking about lepton moments and not hadron moments? And well, first of all, there have been a lot in the last sort of 3-4 years, 2-3 years. There have been a lot of results in leptons, so we're having a moment, so to speak. But also, if you were to look at magnetic moments of the proton, there's not so much to compare it to. Really. So that is except you could look to see whether it's changing in time. But so this is very difficult to calculate a magnetic moment. But an electric dipole moment of composite particles like protons or neutrons or nuclei, those should be pretty close to zero. So we have something to compare it to. And so these, I think, have enormous promise for discovery. We'll hear some talks about that at this workshop. I'm only not including it just because I can't talk about everything. Okay, we're going to talk. I work for the National Institute of Standards and Technology, and by federal statute, I have to use SI units. But SI units come with a hidden shame, something which is just very disgraceful. about them. Everybody knows, anyone who's sensible knows that in a plane wave, the electric and magnetic fields have the same magnitude and the same dimension. It's just obvious, right? It must be true, but SI obscures that fact. It's an unfortunate fact. If you were to use SI units, you would think this electric field and magnetic field, not only are they very different in magnitude, they even have different units. Ridiculous. But we can get around that by just using our own units. Basically, any units you care to name in which, as long as you have units where the electric and magnetic waves have the same dimension and unit and magnitude in electric field, I'm okay with those units. I like volts per centimeter, which are already kind of bastardized units, but all right, fine. Basically they have the same units. Since we know that a field dotted into a dipole moment always gives you an energy, if the electric field and magnetic field have the same dimensions, then the electric dipole moment and magnetic dipole moment must also have the same units. And I like E centimeters, but people don't usually refer to magnetic moments in E centimeters, but you totally could. So for instance, the Bohr magneton is 1.9 times 10 to the minus 11 E centimeters. And just to sort of put you in my units, 1 Tesla is the same as 3 times 10 to the minus 6 volts centimeter. Okay. Given all that, we can now compare electric and magnetic dipole moments in the same breath, which is nice because the experiments are basically exactly the same experiment, right? We put a particle, we put it in the magnetic electric field. The electric field is either parallel or anti-parallel to the magnetic field. We measure a spin resonance. We shine in some radio waves and flip over the spin. We get 2 resonances. The differences between those 2 resonances is the electric dipole moment. The average of the 2 resonances is the magnetic dipole moment. In principle, you can do your G-2 and your EDM measurement on the same day in the same apparatus. As a practical matter, we tend to optimize the experiment for one or the other. Well, let's not kid ourselves. It's the same experiment. And the results can be compared very directly to one another. If you want to make a very good measurement, whether it's electric or magnetic, you need to have a really big field so that you're sensitive to small moments. You want to have a long coherence time, so you have narrow resonances. And you want to have a really large cut rate so you can split the line really accurately. And so this is a figure of merit which applies, again, electric dipole moments, magnetic dipole moments, aka G-2. And so we've had recently these 3 great new results. There's an electric magnetic dipole moment from Jerry Gabriels and his group, formerly at Harvard, now Northwestern. A muon experiment out of that place in Illinois, which is close to Chicago, Fermilab, thank you. And then the Gila electric dipole moment and the Acme electric dipole moment. I'll be using these experiments almost interchangeably in that they have very similar results, but the technologies are a little different. There are 2 of the experiments use trapped ions, or trapped charged particles. The G-2, the electron, is a trapped ion or electron. We use trapped ionic molecules. The muon, well, I guess you could call it a trap in that the beam goes around and around in a circle. If it's a trap, it's a very large trap. The Acme is most distinctly a neutral molecular beam experiment. So appropriate since the experiment is done, well, for many years it was done probably within 50 yards of Ramsey's experiments in molecular and beams and so on. Okay. We can sort of sort these experiments by the strength of the field. The EDM experiments, this is what sort of gives them a lot of their sensitivity, have much larger fields than the MDM experiments. Remember, electric and magnetic field have the same units, so we can do this. Coherence times tends to be much longer in the trap experiments, whether it's the electron magnetic or Gila EDM. The count rates, well, they're going to be low in the electron G-2 experiment because it's done with only 1 electron. It's going to be very high in a neutral molecular experiment because there's no space charge. Muons are sort of rare particles, sort of intermediate. We're kind of intermediate. We have a relatively long coherence time. We have lots of ions, or 200 ions, so we only get to look at them every 3 seconds. So the count rate turns out to be about 60 per second. You'll notice that I look down the various columns and I circle the ones which are large. And you'll notice crudely, both of the EDM experiments have two relatively large numbers. These have relatively small numbers. No surprise then that the absolute accuracy of the electric dipole moment experiments is about 1 million times larger than the magnetic dipole moment experiments. No, sorry, 1 million times better, I should say. How does our experiment work? Just zeroing in a little bit on the electric dipole moment experiment. We have a very large ion trap. For those of you, we're surrounded by quantum information. We're in the quantum information building, for goodness sake. And ion traps have gotten very small recently in that business, sort of 500 micron ion traps. This is old school, right? You can see this is the SI unit for 6 centimeters long. It's an artifact. We're trying to move on to. Okay, but it's a very large electrode with these 8, it's a linear pulse trap. There's 8 rods instead of 4, so that we can create both a quadrupole field and also a rotating electric field, which I'll come back to. We can trap thousands of ions, and because of state preparation limitations, we can count about 100, several hundreds of ions on the side of a Ramsey fringe shot. We start with a neutral beam of hafnium fluoride. As it passes through, check this out, bam, we ionize it. Whoa, look at us. Okay, that's what we're looking at again. Here comes the photoionization beams, bam, and they're left behind. We trap them, we turn on the trap. We do a lot of stuff to it. We have about, on any given day, we have about 8 tunable lasers for photoionization, for photodissociation, for many internal states of optical pumping. Alas, these molecules have a very non-diagonal Frank-Condon matrix, so we have to have multiple pumps, lasers for repumping vibrational levels and for moving them around in the Zeeman manifold, and a very elaborate sequence of pulses and so on to do what at the end amounts to just Ramsey spectroscopy on the spin. But to get there, it's a lot of steps, which I'm not going to spend a lot of time talking about today, just because it's pretty specialized. I love to talk about it. Come see me and we'll talk about the Agile EDM experiment for as long as you like. The molecules, although they have internal to the molecules, there's a very large electric field. In the lab, in the absence of a bias field, the molecules have no particular preferred direction. They're in states of good angular momentum. We have to apply an electric field to make the molecules all line up. Now in the lab frame, we have this large internal electric field in the molecule, which allows us to get this electric field may be only 20 or 30 volts per centimeter. Inside it, it's 20 or 30 billion volts per centimeter. So we get a factor of 1 billion enhancement of electric field by applying this electric field. But because we are working with trapped ions, if you apply an electric field to trapped ions, what do? They fly away. Okay, so the solution to that is we make our electric field rotate, and it rotates slowly enough that the molecular axis can track it. And so we do our spectroscopy in the lab frame, but it's a rotating lab frame, if you want to think about it that way. So we basically do the spectroscopy in this rotating frame. The electric field rotates rapidly enough that it tracks out a circle about 0.5 millimeter in diameter. So just as you can think of Fermilab as being a very, very large ion trap, 40 meters in diameter or whatever it is, we are actually a very, very small electron storage ring. Our storage ring happens to have 1 millimeter in diameter, but it's a heavy ion storage ring, right? These are nothing if not heavy ions. And we do the experiment with the magnetic field pointing with and against it also rotates and it points against our electric field. And this way we do what amounts to a very traditional dipole moment experiment. It just happens to be spinning around in a circle. We had a big result from data collected in 2022. We took the data blind. This little histogram here, it's counts, but actually each of these counts is, I don't know, it's like a 10-minute block or something like that. We took 600 hours of data over the course of several months. We took the data blind. This particular collection of data has a mean of 0 by construction. We just basically subtracted out the 0 from the blinded data. We saw that we had very good statistics. We came up with a good statistical estimate for our frequency. It's like just a few tens of microhertz. We can convert that by knowledge of the internal electric field into error bars on the electric dipole moment. And then one fine day, we look and see what the value was. This was like one of the tensest and most exciting moments in my professional career. Here we are. And I want to particularly call out Tanya Rusi and Luke Caldwell and some senior people on that project. We unblinded, and at the time, we were staring down the barrel of an extraordinarily precise acme measurement, which was shown here with its error bars, which are essentially consistent with 0. And we knew ahead of time that our error bars were going to be about a factor of 2, almost 2.5 smaller. And it occurred to us that it would be perfectly reasonable that our value could be way out here somewhere, which is to say, in agreement with the acne result, but 4 or 5 sigma different from 0. So of course, also it could have been way out here, very, very different from 0 and very, very different from the acne result. We didn't want to do that because John Doe is our friend and we didn't want to embarrass him like, or maybe it's because we had a huge amount of respect for the acne group and it would have been terrifying to have a result which did not agree with them. So we were kind of hoping for this value here. Instead, we got this value here, absolutely the most boring possible value in good agreement with acne, but also in good agreement with 0. But it's a factor of 2.5 smaller. Typically, you report these things in terms of a 90% confidence level on the 90% confidence level on the absolute value. And it's now, you can say it's, if the electric dipole moment exists at all at the 90% confidence level, it's less than 4 times 10 to the minus 30 centimeters. All right, so that was now appeared in Science Magazine a summer ago, 14 months ago. I'll tell you about what we're doing now, but first I want to sort of put this in context of the other dipole moment experiments. How do these experiments compare in terms of looking for fat particles? This plot is a little bit out of date, but it comes, we just heard from Saida's group Saida stuff just recently that you can compare G-2 experiments, this is the case of the electron G-2 experiment, with the value you would predict from the standard model if you happen to know what the fine structure constants is. And on the left, you see the value predicted if you're using the current value for rubidium. Over here, the current value for cesium. The reason why these points come in pairs is I think there's a tiny bit of controversy or ambiguity about how the calculations are done, but you can see these are not very big differences. And yeah, obviously the fine structure constants are in some tension with each other and modest tension with the G-2. This is basically the standard model background coming back to bite us. Although I think, as we heard from the previous talk, there's every reason to believe that this tension is going to get resolved in the next year or two. There is a similar tension going on with muons. In the muon case, the standard model background is not the fine structure constant, but a QCD background. I learned only a week ago that there's up-to-date results which may largely resolve the tension with the QCD background with a hopefully improved numerical calculation of the QCD effects. But for now, I'm going to go ahead and imagine that the standard model background things are resolved, as I think they will be in both cases, and just do a comparison just based on the raw the error bars from the experimental, just looking at the error bars from the experimental measurement of electron G-2, muon G-2, and electron EDM. Okay, so we're assuming standard model is fixed. A way of thinking about this in quantum mechanics 3 or whatever the graduate course you took was called, we learned that for calculating the G-2 of the electron can emit a photon, interact with a magnetic field, reabsorb that photon, and this gives you a correction on order of the fine structure divided by pi. You can generalize that. Instead of having this be an electron and a photon, you can generalize that to being more exotic particles, which I call A and B. The electron splits up into an A and a B, interacts with a magnetic or an electric field, and then reabsorbs the A and B, it becomes an electron. And you end up getting something which looks very much like that. If you make the simplifying assumption, this is basically a calculation I got from Matt Reese. It turns out that the calculation gives you exactly the same value, whether you're trying to calculate the electric dipole moment or the magnetic dipole moment. You've got a term of alpha, because after all, this is an interaction with an electric or magnetic field. You've got a scale term. You've got a term which is proportional to the mass of your lepton and a mass of these hypothetical particles. In this simplified model, you assume these particles have about the same mass. It turns out not to depend on that very sensitively. The mass of your hypothetical new particles, and the only difference is one of these things relies on things which are maximally CP violating, one which are maximally CP conserving. So there's a cosine and a sine of that angle that comes into it. So, but other than that, it's the same prediction, and you can invert that prediction. If you see something which is consistent with 0, you can convert the prediction, and based on the error bars of your measurement, you can put a limit on the masses of hypothetical new particles based on the mass of the lepton you're using, and then assumptions which have to do with what you know about CP violation and how strong this interaction is. I find this very gratifying. It's like particle physics I can understand. There is more particle physics which I cannot understand that I learned from John Doyle from Matt Rees, which involves two loops. It's a much more general thing. It tends to have lower sensitivity in terms of the mass that you can probe, but much more generality in terms of the shapes of and kinds of physics of hypothetical new particles you're sensitive to. But I'm just going to concentrate on this for now. What does this get at? If we compare the experiments, if we look at the relative precision, electrons and muons are enormously sensitive experiments. The electron MDM magnetic moment may be relatively speaking, the most sensitive measurement ever made that you can compare to the standard model. EDMs the answer is consistent with 0, so the ratio of the answer to the error bars is 1, right? So that's not equally impressive. In absolute terms, the EDM experiments are about 1 million times more sensitive. If you take into account the fact that the muon is heavier than the electron and so on, and ask what is the masses we're sensitive to, we are sensitive to masses which are about 1,000 times more sensitive than the electron, G minus 2, about 300 times more sensitive than the muon, G minus 2. If we go ahead and say that this interaction term is something like alpha, the fine structure constant, we can actually put numbers on it. 40 TeV, that's pretty impressive. Ouch. We killed the owl. It had a cost. It was eyeing me. I could see it. We can, but this is for a particular value of this interaction string. We can sort of say, well, like the accelerator people, we're looking for kind of things in the range from weak interacting to strong interacting, just like the accelerator people are. And that gives us sort of a range of what we're sensitive to, quite a bit higher on the high end compared to the LHC, which is in around 2 TeV. But again, subject to, for various reasons, to a range also depending on what interaction strengths they calculate. The big difference is that the G minus 2 people are looking for things which are CP conserving, and we are looking for things which are CP violating. I'm not sure whether I have the sine and cosine right there, but imagine that, okay, we know that electric dipole moments violate CP, magnetic dipole moments don't. Collision experiments don't care about this particular symmetry, and so the LHC is sensitive to both. And then what have I left out? Standard model background issues. We really have no standard model background issues in the EDM. In muons, there's like interactions with QCD. Electrons, there's a fine structure constant. How about the Large Hadron Collider? Do they have to worry about standard model background? Any particle physicists here? Yeah. Basically, if you are a particle physics postdoc, you spend every living day of your life thinking about standard model background. So yeah, the Large Hadron Collider. For those of us in the precision measurement community, sometimes we feel insecure or inferior compared to the particle physicists because we have to subtract out the standard model. They have to subtract out the standard model. They see like they have these things called vetoes and gates and triggers and things like that. It's like basically 1 part in a trillion of what's left over is maybe new physics. So many issues. Okay, we're going to play a TV game, which I'm going to call Bug or Feature, Feature or Bug, and I'm going to be the host of this game show. Here's Eric. Okay. The electron magnetic moment has standard model sensitivity to experimental value of alpha. This is a bug. Maybe. I think that the electron magnetic dipole moment has the best fractional sensitivity of any measure, which means it's going to be, you can use it, for instance, to measure alpha better than any other way. This is a feature. And more generally, if you have anything that looks like sort of a multiplicative correction to the standard model or a limitation to many loop perturbation theory, the electron G minus 2 is a thing. And moreover, I recently learned that you can actually use the G minus 2 contribution as a limit to weakly interaction on low mass bosons. That stuff which was over on the left-hand side of my standard model feature. Muon MDM has sensitivity to uncertainties in standard model QCD predictions. This is a bug vis-a-vis electron MDM. No, it's not. The reason why the muon MDN is more troubled by QCD corrections is because the muon G minus 2 is more sensitive than the electron G minus 2. If the electron G minus 2 experiment gets to be 10 times more sensitive, and I'm sure it will be, then it will be pretty much equally sensitive to QCD. So it's the electron people only don't have to worry about it because they haven't gotten there yet. When they get there, they'll have to worry about it. Electron EDM, which is our business at Gilla, has basically no sensitivity to FM background. This is a feature. Nah, not really. The only reason why EDM is so insensitive is because we can't see CP violating, which CP violating physics, which the standard model has so very little of. We are blind to CP preserving new physics, so you could call that a bug. This is the contrarian thing here. Electron EDM can look deeper into the extra fat exotic particle parameter space. This should have a little trademark next to it. Extra fat. Maybe I should come up with a better acronym. Anyway, electron EDM can look deeper into extra fat exotic particle parameter space than can the Large Hadron Collider, and much deeper than the D-2 experiments can. This is a feature. And I say, yeah, okay, I'll go ahead and take that. It is pretty rad. That's pretty great. So that's where we're at. How much time do I have?
13.
Good. So far, up through, this is sort of brought you up to date through about 2 years ago. We already have sensitivity, depending on models, which are quite a bit better than the Large Hadron Collider limit. If we could do another factor of 10 in sensitivity, that would give us almost in a very model independent way. Whatever your model is, if you do another factor of 2 in sensitivity, you get another factor of 3 in mass reach. Suppose you read in the paper tomorrow, Large Hadron Collider found out that they had the energy moderator feature on, and they took it out, and all of a sudden they went from 14 TeV to 52 TeV. That would be a huge deal. Oh, by the way, and the brightness went up a factor of 9, so suddenly they're able to access. That would be the biggest news in particle physics, right? So what I'm telling you is if we get another factor of 10 in sensitivity and dipole moment, it's a big deal in particle physics. And it's coming soon, as it turns out. You can tell that from this plot, this sort of Moore plot here, which has absolute positive determinate predictive features to it. This is the sensitivity on the electric dipole moment over the years. A lot of times it was done in vapor cells, and then it was done in beams. Came the onset of the first molecular experiments by the Heinz group and Imperial, Yale first and then Imperial. We've been playing sort of leapfrog with the ACME people. It's amazing that our experiments are really quite different in terms of count rate, in terms of coherence times and everything. And yet we've been sort of within a factor of 2 or so of each other right on time. The ACME group, by the way, we're currently a little bit ahead of the ACME group. The ACME group will almost surely have a new improved result sooner than we have. Around Gilla, we call this the onset of this result, which is coming soon. The Empire Strikes Back. And then when John Doyle comes to visit us and comes to the lab, we always hear the Star Wars Imperial Emperor themes. And so that's happening soon. We will probably need, and I can see hard to know, but probably several years later. The ACME group is due in the next 2 or 3 months. Do I have that right, John? No. Well, certainly by next summer anyway. Yeah. I'll give you an update. We'll be at least 3 or 4 months behind that. But anyway, could be a big deal. How are we doing towards that? Already we are, what sort of sets us, our sort of really singular features, we have compared to other EDM experiments anywhere, we have very long coherence times. We are doubling down on this. We like coherence times, both in terms of the sensitivity, but also in terms of longer coherence times give you narrower lines, generically gives you better ways of, narrower lines are better at rejecting systematics. A lot of systematic errors are line shape errors. If you have a narrower line, you're less sensitive to line shape errors. So we're planning to go to to get to the longer coherence time. We swapped molecules. We went from hafnium fluoride plus to thorium fluoride plus. Thorium fluoride plus is a heavier ion. Because it's a heavier ion, there's more fine structure constant. That fine structure energy that turns to push one of the electronic levels where our science signal lives down to be the true ground state. And hafnium fluoride plus, our coherence time was limited by our 3-second spontaneous lifetime. And so it's a very, very forbidden transition. 3 seconds is a long spontaneous lifetime, but it still happened, and that was exactly no coincidence. At the end, by the time we worked and suppressed all other sources, the last half of our data was taken with 3 seconds spacing between the two Ramsey pulses. But now we no longer have spontaneous emission, which means the coherence time will be infinite. No, it won't be infinite, but it will be longer, right? We'll find out. Oh, turns out that the coherence time is now getting close to 8 seconds, and it's hard to see wiggles here. This is in our new thorium fluoride plus experiment. We're now out to decay of coherence. Seeing coherence all the way up to about 8 seconds. We think this is the longest coherence time ever seen in a molecule. But we're greedy. We have done calculations. We think we should be able to get out to 20 seconds. So we're aiming for that. Here's the group as it's currently configured. Actually, no, this picture is already a little old. You saw the group a little earlier. I show this picture because we have even a bigger, you can see the 8 long rods of a linear Paul trap. These little discs that go this way divide up, provide many sort of end caps. It's like there are many different end caps. And by applying a sort of sinusoidal worm gear voltage off of those, we can sort of create traps, and we can adiabatically move the ions up or down. In fact, we can make multiple packages of ions and move multiple packages of ions along in the trap. The plan eventually is to make the ions, move them in, apply a pi over 2 pulse, move them further along, apply another pi over 2 pulse, and then read them out, but have perhaps 20 packages of ions traveling along in parallel. And we're sort of reading them out in an interleaf way, which gets rid of Dick noise. What's the term I'm looking for, Jim? Isn't that what it's called? Yeah, Dick noise, not Dicky, right? Dick noise. We're working on suppressing that, and also just having more signal noise, because instead of getting one package every coherence time, we're sort of doing experiments in parallel. So all that's coming on. We've been able to make atoms here and then have them travel along apply a pi over 2 pulse, have them travel out, have them come back, have the coherence all preserved inside. Coherence is preserved as they move along in the shaft. You can think of it as a beads experiment, except the speed is about 10 centimeters per second. So it'll take about 20 seconds to travel the length of the shaft. What difficulties do we have in getting to 8 seconds, and what new difficulties do we have in getting to 20 seconds? This is what I forgot to mention is out here where we make the ions, it's at 300 Kelvin. Deep down in the trap, it's about at 170 Kelvin. You might think 170 Kelvin, that's your cryogenic temperatures. That doesn't sound very impressive. It turns out we just need to have the black body radiation red enough that it doesn't excite the first vibrational transition. And the first vibrational transition is at like 900 Kelvin or something. So you go from 300 Kelvin down to 200 Kelvin. It's a very large exponential suppression of the spontaneous decay. So this is the effective temperature, 300 Kelvin where we make them, 150 Kelvin deep down inside. This green line, this blue line is the predicted black body contribution to decoherence. And you can see that we see something like that, except the coherence is offset upward. So basically, as we move the ions deeper and deeper into the trap, the coherence rate goes down, but it's offset up by some other contribution to decoherence. So you can see, yes, it's working very well at suppressing the thermal contribution to the decoherence. Various forms of collisions are our current issue. The two ions don't really collide in an atomic physics sense. So, you don't have atoms, with atoms and neutral atoms, neutral molecules, they come together, they bash into each other, all kinds of weird chemical stuff happens. That doesn't really happen. Okay, but with ions, as they come closer to each other, they repel each other, and the electric field from one ion is felt by the other ion. It causes the electric bias field to tilt a little bit, which eventually gives rise to a Berry's phase effect, which causes decoherence of the phase. I'm not going to walk you through this, but we've studied this as a function of confining frequency and ion number. Also, if there's background neutral atoms and they come zooming by, not too close to our ions, they apply a little pulse of electric field as well. I'm not going to go through that, but we're studying that. We have problems. 170 Kelvin is not cold enough to freeze out hydrogen by any means. So we have problems, especially with hydrogen down the end of our long steel tube. The new tube will be made out of titanium, which will go a long way towards suppressing the hydrogen. I don't want to say much more about that. A dark secret about thorium fluoride plus is that it's not very, our main readout method is photodissociation. We had bad efficiency of photodissociation. We just spent, we've recently joined a collaboration of folks who are interested in thorium fluoride plus, including Xing Fan here at Harvard, Jiaobu and Stefan Malbrunot at Triumph, who are, this group is working on radioactive thorium fluoride plus for shift moments. We're working on EEDM. We all like thorium fluoride plus, and we recently did, like, I think 6 weeks or something like that. So many hundreds of hours of survey spectroscopy, and the great result of that is hidden behind here. But in fact, we now have detection efficiencies, which is up by about a factor of 7 or 8, which sounds great. But it's not up by a factor of 7 or 8 compared to hafnium fluoride plus. It's up by a factor of 7 or 8 after thorium fluoride plus went down a factor of 7 or 8. So this factor we lost, we've just succeeded in gaining back. I wish we had done this work 2 years ago, because we would have had 7 or 8 times more signal on the new progress acid. We're working on various things to deal with it. I guess I want to emphasize again, this factor of 10 is coming, not factor of 10, something close to it, which would be a very large increase of reach in terms of the fat physics, accelerator type physics, parameter space for new particles. And once again, this could be part of you. This is my email, but you can find me easily on the internet. Let me know if you're interested. I thank you for your attention.
Hey, Todd, I'm wondering what your one sentence explanation is for why the EMBM has worse absolute precision than the EMBM.
Well, most of it is a strength of the field, right? Our field's like, well, one is the strength of the field. We're 1,000 times larger field. The other is that the magnetic dipole has one particle of a trap at a time, and they have a terrible duty cycle. Like, they measure and then let it ring down for like 2 minutes. So it's kind of like one particle every 2 minutes or something like that, which is a hard way to earn a living. Those two things combined are a bunch of it, and on top of that, they're not even statistics limited. So you put them all together, and I think that gets you well in the direction of 1 million anyway.
Yeah, I was thinking, if you can imagine the electron inside the molecule, it's seeing the atomic unit as a magnetic field.
Yeah, okay, so in a plane wave, the electric and magnetic fields are the same. In a molecule, there's a factor of alpha in there. You know that.
Yeah, I want to make my color commentary. When you put up the plot and said, okay, we're going to keep on improving the EM, and as a function of years, so we're going to keep on going. And I heard a couple of little chuckles, when you said that, because it's like, wow, you don't really know that. One of the things that I say, I won't say tomorrow, the opportunity to say it now, we're basically following clock technology. So anything that happened 20 years ago, we're more or less now applying it to doing these kinds of precision measurements. So what it means is all you have to do is look back, and is clock technology improving? It is. It is in fact on the same slope.
You heard it from the expert right here.
So just a comment on this, the very same plot. So can you show it maybe? So this is this progression plot.
I could get rid of the smiley face if that helps. Nope, what have I done? Sorry. Okay, I seem to have come out. Which picture did you want?
What John just.
Oh, yeah, you're talking about the Moore's Law plot here. Yeah, okay, let's find Moore's Law.
Right, so if I look at this, so it seems like you are making about 5 orders of magnitude improvement for every 30 years or so. Is it right? Yeah, right.
Sure.
So, the current value of, electron EDM in the standard model is 10 to the minus 35,
Yeah,
right? So it's another, 30 years. So,
sure, why not? Why not? Yeah.
so well, so suppose there is no, new physics beyond the standard model.
We would
At
at
least here, right? So just.
Yeah, Moore's law is not destiny. People, you get, even with transistors, you get to a point where, okay, John's pointed out that clocks keep better and therefore it keeps getting better, therefore per force EDM will get better, and that is the official line, yes. So, yeah, I like to see, I see some structure in here, like this was, I see it as like impulse improvement. This was the onset of molecular, instead of doing it in cells, you did it in boom, and then it was kind of saturated. Here come molecules, boom, kind of saturated. Maybe we need like polyatomic molecules, I don't know, something, one other, something, one more step. That will be like, this is diatomic molecules, here come polyatomic molecules, something along those lines perhaps. We need a new kick,
Now we need a coffee break.
and a coffee break.
You can ask Eric more questions during the break.